Hi, this is Nolan, and I'm going to do a demonstration of the original functionalities of a simulator put together by the Verifiable Robotics Research Group at Cornell University. This simulator is used to simulate the iRobot Create and is used for a course taught by Professor Kreskazit. And I later worked with Professor Kreskazit to add on multi-robot functionality to the simulator. The original simulator can be called with the simulator GUI command, and it brings up the GUI where we can see we have a model of our create robot in the center. The first thing that we're going to do is to load a map into the simulator. The map that I'm navigating to has been pre-created, and it is a text file that is parsed with information containing the locations of wall vertices. Now, if we try and drive the robot using the manual control into a wall, we can use these buttons to assign it rotational velocities and forward velocities. We'll see that the physics engine causes the robot to slide as it would in reality. Let's back the robot off the wall a little bit. Now we can also get sensor readings. The other sensors that are useful for simulation are the bump sensor and the LiDAR sensor. The bump sensor is approximated to be the forward 180 degrees of the circle that we're using to model our robot, and the LiDAR provides 360 degrees of distance measurements. Now, it's possible for us to load a configuration file describing any uncertainties, time delays, and Gaussian distributions of noise to these sensors. This is most applicable to the sonar sensors since they obviously are not perfect in real life. So when we load a configuration from this same homework assignment, homework for config, you'll see that our measurements of the sonar now have quite a bit of noise. The three sonar behind the robot are at their maximum range. If we start rotating the robot, we can see that those readings update. Finally, for the original simulator, we can load an autonomous motion control program. We can click here to save any sensor data from our robot during the autonomous run. So I'm going to select a simple motion control program that records data as the robot moves, and if it happens to hit a wall, it simply backs up, turns by a pre-programmed value, in this case it's 95 degrees or so, and then continues to drive forward. Once the robot is finished, we can click the stop button, and we could run some sort of post-processor on the sensor data. This could be like an extended Kalman filter, a particle filter, or a mapping algorithm. And we can save our data as demo sonar. Finally, it should be noted that while in the autonomous mode, the simulator can access the real-time sensor data. So it's possible to run algorithms like SLAM or anything that depends on the current position of the robot. The simulator also can record the actual global position of the robot, so it's possible to compare the current position in the simulator with the robot's position estimate of where it thinks it is.